Here is assignment 6.3. So this lesson was on the trapezoidal rule, using trapezoids as a way to estimate integration. Use the trapezoids used to the right to approximate the integration from 1 to 7. So here's one trapezoid, and again I just need to know the formula, which is a triangle. Half the bases, so this is up on its side, so the bases are pointing up. So 1 and 3, that makes 4. And the height is actually the width of it from 1 to 2. That's 1. That's it. Keep going. The bases are pointing up. So that is 3 and 2. I think that's 5. The width is the height. So that's 2. One more time. The bases are pointing up. So that's 2 and 1. That's 3. The width is the height, so from 4 to 7, that's 3 again. That's it. I don't even want you to simplify it. We're done. That's it. Number 2. The graph in the figure below was recorded by an instrument using a physical quantity. Approximate the area of the shading region using a trapezoidal rule and let n equal 6, which means there are 6 equal trapezoids. So if they're all equal trapezoids, we can set this up. We know, first of all, that the formula is 1/2 times the width or the height. And if it's 6, 1, 2, 3, 4, 5, 6, each width then would be 1. So you can go 7, take away 1, divided by 6, or whatever the height of each trapezoid. Or the width is 1. And then the rule for multiple trapezoids of the same width or height. Take the first height, which is, what is the height at 1? 5. Then the next height at 12, you double it because you need it for the first trapezoid and the second trapezoid. Plus double the next height, which is 28, because you need it for both. It's shared. Double 34, because that base is shared. Double 15. And then double 25. And then the last one, 20, don't double because it's not shared. It's only used by one trapezoid, and that's done. This is what it looks like. Don't even bother simplifying it. But there, the formula is 1/2, and all the heights or widths are the same. So they all share 1. And then the bases, if they share a base, then you double it. So the very beginning and the very end are not shared. Everything else is doubled. All right, number 3. The points shown are from a continuous function. Use the trapezoidal rule in the table and the trapezoidal rule with 4 equal subdivisions to approximate the integration from 2 to 4. So to find the width there, first of all, it's 1/2 times. So the height or the width of it would be 4 take away 2. So the upper bound subtract the lower bound. And then divide it by how many you have, which is 4. So if I put that together, the width of each one is 0.5 or 1/2. So every 0.5, I'm going to get a height. So the first height is right there, 4.12. And then I'm going to double at 0.5. That's 3.21. I'm going to double the next 0.5, which is 3.94. And then I'm going to double again, 4.69. And then the last height, which is at 4, it's a single one. It's not shared. So once you get used to the pattern, it's pretty simple. Oops, this one. So 1/2 is part of the formula for a trapezoid. The width or the height of each trapezoid, the upper bound subtract the lower bound, divided by how many trapezoids you want, which is 4. So that's 1/2. And then you just count 0.5. This is what you keep counting by. So it's 2, then 2.5, then 3, 3.5, then 4. And just remember the first height and the last height are single, and all the heights in the middle are doubled because all the heights in the middle are shared bases. That's it. Don't even simplify it. Number 4. A man-made lake has the shape illustrated in the figure with measurements 20 feet apart. Use the trapezoidal rule to estimate the surface area of the lake. So already, I know the formula is 1/2. They're 20 feet apart, so that's the equal heights or widths of each one. And then these represent the bases. So we start with 55, and then we double 63. You double 63, we double 81, we double 86, just get used to the pattern. We double 106, we're not going to simplify this, double 118, it's going to run out of space, double 98, double 57, double 47, and then the last height is like 0. So if you think of the very last width there, it's like 0. You can use 0 for that last one. But it's important that you double 47. 47 is not the end of the lake. And this is what it looks like following the pattern. So the formula starts with 1/2, the equal width or height of each trapezoid, and then the pattern, the first height and the last base, they're singles. Everything else is doubled because they are shared by 2 trapezoids. Number 5. In number 5, for problems 5 and 6, use the trapezoidal rule with 4 equal subdivisions. So if I want to find the width or the height of each trapezoid, you would get the upper bound, subtract the lower bound, divided by 4. So for 5, it's 1. So if I'm going to estimate from 0 to 4 the square root of x squared plus 1 dx, the formula starts with 1/2, and then the width of each trapezoid is 1, and then the heights. So I'm counting by ones for my bases. So I start with 0, so plug 0 in, and you get the square root of 1. Plug 1 in, and you get the square root of 2, and you have to double it. Plug 3 in, and 3 squared is 9 squared, plus 1 squared is 10, and double it. And then plug 4 in, and singleton, so that's the square root of 17, but it's not doubled. And that's it. Oh, draw an accurate sketch. I'll try. So 0 gives you the answer 1. And all the rest are square roots now. Square root is 17. It kind of looks like this, actually. I'll show you. Let me show you my work. So this is kind of the curve. It actually is concave up because of the x squared. So think of it in terms of that. 4 trapezoids. And you take each height. This is what it would look like right here. So it starts with the top bound, subtract the lower bound, divided by 4. That's the equal width or height of each trapezoid. The formula starts with 1/2 times that, and then each height or bases. The first base is not shared, and the last base is not shared. Otherwise, the ones in the middle are doubled. To number 6. So again, here, let me just show you my work from the beginning. To find that height of each trapezoid, you take the top bound, subtract the lower bound, and divide by 4, because we have 4 trapezoids. So that's 8 divided by 4. So it's every 2 where we count the heights. And so the formula is 1/2 times the height, which is 2 for each one, and then the bases. Well, to find the first base, you plug in 3. And you don't even have to simplify it. Like, you can just do this. Oops, if I can write the number 3. The second one, we're going to double it. So if I'm going by 2's, the next one is 5. And then the next one's 7. And then the next one's 9. And then the last one is 11. And it's single. So only the ones in the middle, you double the bases because they're shared by 2 trapezoids. So the very first and the very end, they're singles because they're not shared. What would the graph look like if I just sketched it? So from 3 to 11, 3, 4, 5, 6, 7, 8, 9, 10, 11. So at 3 take away, the answer is 1. Here, I'll do it up here, 1. And this is a decreasing function from there. There's an asymptote at 1, just so you know, so that it would go up forever for there. But from 3 to 11, and then you can see the trapezoids that are created. It's the most accurate way to estimate an integration is using a trapezoid. A rectangle always has like an over or under estimate more than a trapezoid, which is usually pretty tight to the curve. All right, number 7. In number 7, it says now use Riemann sums. So now we're back to rectangles for number 7. So I want to integrate from 0 to 8 f of x dx and use a midpoint Riemann sum, and n equals 4. So the width is going to be the upper bound, subtract the lower bound, divided by 4. And then a midpoint would be, let me show you my work, write down this. So x squared subtract 8x plus 17. So the upper bound subtract the lower bound divided by 4. That's how many rectangles you have. This formula does not start with 1/2. It just starts with 2. That's the width. And then it's just each height. So the first height would be at 0. So if you plug 0 in, you get 17. The next height, we're counting by 2's. So the next height would be at 2. So plug 2 in. If you're not in the mood to simplify it, I don't blame you. So you just plug 2 in. The next one would be 4. The next one would be 6. And then the last one would be 8. So again, I plugged in 0, 2, 4, 6, and 8. So that makes up the, whoa, I made a mistake. What? Okay, it's a midpoint, right? And I didn't do a midpoint at all. I wasn't even thinking. I should think first, shouldn't I? So ignore this. This part is good. Top subtract bottom divided by 4. There's 4 rectangles, and there's a width of 2 for each one. And if we're using a midpoint, then I have to think more. So if I'm going from, and if I visualize it, if I'm going from 0 to 8, and I'm counting by 2's, I wasn't even thinking, the midpoint here is what I need to plug in. So if I need to visualize it, it's 1, 3, 5, and 7. That's what I need to plug in for my 4 heights. So if I did it properly and thought about it, it'd be 2, and then you plug in 1. Then you plug in 3. Then you plug in 5. And then lastly, you plug in 7. That's a midpoint. And I wasn't thinking. Sorry. So for a midpoint, you'd use 1, 3, 5, and 7. That's better thinking than what I did before I just went into the problem. Do you know what this was that I did? Is I did a left Riemann sum, 0, 2, and then I even added an extra rectangle at the end. Just wrong and all together. Let's do it right. Number 8. Let's see if I can do better. So, oh, it's a left hand. I already did the work. So that was the answer. That's left, where you use 0, 2, 4, and 6, and not 8 scratched down. That's his life right there, isn't it? So 0 to 8, f of x dx. I just did it already. This is a left-hand one, what I scratched out. So, again, the width is 2. You start with 0, then 2. Then 4. And then 6. Don't go past 6. And there's your 4 rectangles. Yay. Comes around. So that's called a left Riemann sum. Again, if you want to visualize it, counting by 2s. So these are the rectangle bottoms of the rectangle. So left would use 0, then 2, then 4, then 6, and would not use 8. A right would use 2, 4, 6, and 8. Middle we just did, and so on. Okay, number 9. Keep trying to do better. Number 9. So we're integrating from 0 to 9, x squared subtract 8x plus 17, and use a Riemann sum with 3 inscribed rectangles of equal width. And why is this such a poor approximation to do that? So if they're inscribed, so if you're going to use a Riemann sum with 3 inscribed rectangles, that means they're using the points on there. So if you used, first of all, the width of each one, top subtract bottom divided by 3. So 9 take away 0 divided by 3. So the width of each one is 3. And then if you inscribe it from 0 to 3, from 0 to 3, the height would be 2. From 3 to 6, the height would be at 4, which is what, 1? It's really a lower Riemann sum. And then from 6 to 8, you would use, plug in 6, that'd be like 5. So the reason it's so poor is that it covers so little of the act. There's so many gaping spaces that it's a really bad approximation. So if you, the first one you'd actually, so you keep plugging in the smallest number for the inscribing part. So from 0 to 3, the smallest y value there is 2. From 3 to 6, the smallest y value there at 4, which is 1. And then from 6 to 9, the smallest value would be right there, that y value right there, which is 5. The graph of it this is what it would look like. Let's count to 9. 1, 2, 3, 4, 5, 6. So this is what the sketch would look like, because 9 is higher than this. And then the first one from 1 to 3 would look like this. From 3 to 6, it would look like this. And then from 6 to 9, it would look like this. And why is that such a poor approximation using that? Can you see how much is left that you didn't find? It's a large. It's called a lower limit Riemann sum. So using a lower limit Riemann sum results in a large underestimate. So the underestimate is really large. There's like a lot of gaps here that it's not even close to the right answer, right? If you like look at it, that we just shaded part of it. There's so much that we didn't find the area of. So it's not a good Riemann sum in this situation. Definitely not as good as a trapezoid, right? All right, number 10 and on. These are review questions. So for number 10, this is the fundamental theorem of calculus, part 1. Part 2, the sequel. Do the substitution. So that's sine 2x, and then the hook is 2, and the derivative was 0, 0. So this is what it looks like. It's just a substitution question, and then take the derivative of the limit as the hook on, and that's it. It's over. Number 11. Same idea. The derivative of a definite integral. This is the fundamental theorem of calculus, the sequel. Again, but this time we're substituting 5 in and taking the derivative. So we have to start with 0. Then we can substitute x squared in, and then the hook-on factor. So that 0 is essential because we're starting with 0 when subtracting. Number 12, the derivative. And I'm integrating from t to t to 2t. I don't know why I couldn't say that. T to 2t. My brain doesn't want to do that. 2 to the x dx. So here's the heart of it. Substitute the upper bound, take the derivative, subtract, substitute the lower bound, take the derivative. It's 1, I don't really need it, and it's over. Number 13. In number 13, it's a calculator question, right? Let's go to the next page. Yep, use a calculator. So let me show you how to use our calculator. Can you do a definite integral with your calculator? I bet you can. Make sure it's in radians. There's my calculator. Where did all that come from? I bet you might. I blame one of my kids. There we go. All right. So you don't even see what I'm doing. There's like a ton of stuff to delete that wasn't deleting. So here, let me show you how does this look? Press menu, press calculus, press integration. The lower bound is pi over 2. So go control, divide, and then go pi over 2. And then the upper bound, I think, is just pi. And then what I'm integrating is sine x. And I'm integrating with respect to x, and I get my answer. Nice, easy answer, too. 1. All right, number 14. In number 14, you're given integrating from 0 to 2 f at x dx equals 4, and that the function is an odd function. That means the first quadrant and the third quadrant, or the second and the fourth, like the cross quadrants, have symmetry. And so if I do a sketch here, from 0 to 2, whatever this area is from 0 to 2, it helps to have a visual of what I'm doing. So let's look at the first one. So I don't really know what it looks like, but if I have a visual of it, it can help me understand it better. So from 0 to 2, if I shade it in, is 4. It's above the axes. So from negative 2 to 0 would be the same area, but below. That's what it means to be an odd function. So this area would be negative 4. In part B, it asks from negative 2 to positive 2. So from negative 2 to positive 2, the area below would match the area above. So if you add them together, it add up to 0. Part C, we're integrating from 0 to 2, but whatever we get, the answer is going to be negative. So 0 to 2, same thing, but the answer is going to be negative because that could be out front. And so instead of positive 4, the answer would be negative 4 because of that negative. Part D, integrating from 0 to 2, and we're multiplying it times 3. So don't make it complicated, just multiply it times 3. So 3 times 4. So we're just going to go 3 times 4, so it's 12. And then the last one, part E, we're integrating from 0 to 2, and it's f at x plus 1. Be careful for this one. Let me show you why. So we have to separate this into two integrations. So the first integration is just f at x, but the second one is 1. So for this one, we know the answer. So from 0 to 2 f at x, we're given it. The answer is 4. But the second one, I have to do the antiderivative, which is x, and then plug in the upper bound and plug in the lower bound. So the antiderivative of 1 is x. If you plug in the upper bound, it's 2, take away 0, or 2. So altogether, that answer is 6. Number 15. Let me look at the question. Number 15, all of these we need to integrate without a calculator. So negative 2 to positive 2, the absolute value of x cubed dx. So to understand this one, if you graphed from negative 2 to positive 2, this is what it would look like. It's an odd function. Now, if we do the absolute value, so this would be this area and this area, but absolute value flips it up. So if I flip it up, these two areas are exactly the same. So in other words, I'm going to integrate from 0 to 2 and double the answer. So if I integrate from 0 to 2 and double this answer, that's the same as the absolute value, which reflects it up, which means both areas are positive, and they're equal to each other because it has symmetry with the origin, x cubed. All right, so that's what I'm going to do to get my answer. So the antiderivative is x to the 4th divided by 4 from 0 to 2. And then you plug in the upper bound. When you plug in the lower bound, the answer is just 0, and there's your answer. You could simplify it. 16 divided by 4 is 4. 4 times 2 is 8. But you can just leave it at that answer too. Done. I just want you to understand how the graph can help support you in this way. Number 16. So I'm integrating from 1 to 3, 1 over t squared. So I'm going to write that as t to the negative 2, t to the negative 2. And this is like, there's nothing tricky about this one. Just the antiderivative. So add 1 and divide, and we're integrating from 1 to 3. And then you plug in the upper bound. You plug in the lower bound. And that's it. If I simplified it, it would be negative 1/3, and negative makes it plus 1, so altogether that would be 2/3, if I had to. Number 17. Oops, I hit calculator. Number 17. So x squared subtract 2x to the 5th, and then x minus 1 dx. How would I integrate that without a calculator? So how I would see it is, what's the derivative of the base? And the derivative of the base is 2x minus 2. So the derivative of this base is 2x minus 2. Look at the hook before and after. So this is the hook I need. So I need 1/2. Because 1/2 of 2x subtract 2 is x minus 1. So they're now equivalent. Then you can unhook it. And then your answer is 1/2. It's x squared subtract 2x to the 6th. And we do need a constant at the end. It's an indefinite integral. Number 18. We're flying like Peter Pan here. So number 18, integrating the square root of y, and then 1 minus 1 over y dy. This is just a bunch of algebra. Can you do this and do this with algebra? So I'm going to write this calculus friendly. That's y to the 1/2. That's 1 minus y to the negative 1 dy. And then I'm going to distribute. So y to the 1/2 times 1 is y to the 1/2. And then when I distribute here, you add the exponents, and it's negative, and it becomes y to the negative 1/2 when you add exponents. Now, you could just integrate by adding 1, and then dividing or times the reciprocal. Same thing here. Add 1, dividing or times the reciprocal, and then don't forget the constant. Number 19. In number 19, it says use geometry to integrate the function shown at the right, and it's a piecewise, and so you have a line, and then you have like a part of a circle there. So it's like a quarter of a circle right there. And it says, can you integrate it using geometry from 0 to 4? So from 0 to 2, it's a trapezoid. That's simple. So from 0 to 2, what is that trapezoid? So the bases are 4 and 2. So that's 6. And the height or the width is 2. So it's 1/2, 6 times 2. And then this is a quarter of a circle. So that's 1/4 pi. The radius is 2. So it's 1/4 pi 2 squared. So there's the trapezoid, and a quarter of a circle with a radius of 2. Half of 12 is 6. 4 divided by 4 leaves me with pi, and you have your answer. Number 20. Just checking. Here's our long question. 20, you have a rate graph. Can you interpret a rate graph? Of course you can. It says, on what interval of time was the car moving backward? And that would be when it's negative. So that's when it's underneath the graph. So that would be from, in minutes, it would be from 0 to 2 minutes because it's below, it's negative. So from 0 to 2 minutes, it's moving backward. When is it moving forward? Well, it's moving forward when it's above. So from 3 to 10. That's moving forward because it's above positive velocity. When is it not moving? When is it resting? Right here, right when it's on the axis, from 2 to 3. So from 0 to 2 minutes, it's moving backwards because it's below the axis. From 3 to 10 minutes, it's moving forward because it's above the axis. Velocity is positive. And from 2 to 3 minutes, it's resting because it's on the axis. The velocity is 0. B. Write a sentence telling what point A represents. So point A is 6 minutes in. So at 6 minutes, what's happening? So at 6 minutes, the velocity of the car is, how fast is it going? It's 6,000 feet per minute. So at 6 minutes, the velocity of the car is 6,000 feet per minute. How about part C? Let's look at that. Find the speed of the car. Remember, speed is the absolute value of velocity, so it's always a positive number. So at 1, that becomes a positive number. So when t equals 1, the speed is what? 1,000. It's positive 1,000 feet per second. At t equals 2, the speed is at 0 feet per second. And at t equals 4, the speed is, so at 4, the speed is 2,000 feet per minute. Feet per second, sorry. Here we go. So at 1, the speed is 1,000 because it's the absolute value. At 2, it's 0. And at 4, it's 2,000. That's it. Part D. So find the acceleration. That is the derivative of velocity. That's the slope. So at 3/6, so at 3/6, what is the acceleration of it? So between 3 and 6, can you find the slope of that line? So rise over run, that's 6,000 over 3. So 6,000 over 3, that's the beginning. So that's rise over run, 6,000 over 3. Did you see my son there? I said, no, go away. So 6,000 divided by 3 is 2,000. Now, the key is the units. So it was feet per minute, but if it's acceleration, it's feet per minute or feet per minute squared. So the key is the units and the slope. E. On what time interval is the car's acceleration the greatest? So the acceleration being the greatest is when the slope is the steepest. So here we have negative. So it can't be negative. So if you have a negative slope, it can't be a great number. So it has to be where the slope is the greatest. And so between 3 and 6 minutes, the acceleration is the greatest because it's the steepest slope, positive slope. So between 3 and 6 minutes, the acceleration is the greatest. It's the steepest positive slope is what we're looking for. For F, on what interval is the absolute value of the car's acceleration? So now when it says absolute value, Now the steepest spot, you take the negative slope and it becomes positive. So now between 9 and 10 minutes. Because that's the steepest in whatever direction you're pointing. So between 9 and 10 minutes, the absolute value of the acceleration is the greatest. G says, on what time interval was the car speeding up? So it's speeding up in two ways. It's speeding up when the signs match. So when it's below and negative. So do you see the negative slope and negative velocity? It's speeding up. So between 0 and 1 minute. That's because the signs match. And it's speeding up when it's positive and above. So between 3 and 6. So between 0 and 1 minute, and between 3 and 6 minutes, acceleration and velocity share the same sign, therefore speeding up. So the idea of speed increasing is that acceleration and velocity share the same sign. That's different than velocity increasing. Number 10, number G, H, letter H. In H, it says integrate from 0 to 10 via t dt. So integrate all from 0 to 10. So let's just break it down to shapes. So from 0 to 10, the first shape I see is a triangle. It's negative because it's below. So half the base is 2. And then the height of that triangle is 1,000. So there's the triangle. The second one is a trapezoid. So the bases are 3 and 7. So 3 and 7, the bases are 10 altogether. So 3 on top, 7 underneath, together it's 10. The height of that trapezoid is 6,000. So you have the triangle and then you have the big trapezoid. So half of 2,000, that's negative 1,000. Here, half of 10 is 5 times 6, that's 30,000. So altogether, that would be 29,000. And in this case, we need a unit. It would be 29,000 feet because it's an accumulator. Now, I'm going to skip, like J says, write a sentence. So I'm just going to skip to J. Write a sentence. What does that mean? So from 0 to 10 minutes, the car traveled a total distance of 29,000 feet because it's an accumulator. So I just did J to begin with. So here, 29,000, what does it mean? From 0 to 10 minutes, the car traveled a total distance of 29,000 feet. It accumulated the distance the car went. But yeah, you know what? The car traveled it's not really a total distance, but a distance of 2,009, and it's displacement, right? Like from where it started to where it ended. So that is actually the displacement of the vehicle. So where did it start? Where did it end? And the answer is 29,000. That's the displacement of the vehicle. The total distance of the vehicle. So the second part, I, which is the absolute value. So the absolute value for I is you take that area of the triangle and it becomes positive. So now when you add it up and it becomes positive, so you're integrating from 0 to 10, and it's the absolute value, so it all becomes positive. So now we already did the hard work, so you don't need to do it again. So instead of negative 1,000 plus 30, you add them. Oops, this should actually be then 31,000 feet if you add them together. Now this one you would say is total distance. So from 0 to 10 minutes, the total distance, because the absolute value gives you total distance, just velocity gives you displacement. So the total distance traveled was 31,000 feet. All right, that was a long one. Two left, 21 and 22. 21, the product of two positive numbers is 80. So I'm going to let x equal the first positive number, and then y is going to be the second positive number. The primary equation is what I'm looking for. So find the number so that the sum of the first and 5 times the second is a minimum. And then I need a secondary equation. And the secondary equation is the first sentence. The product of the first two numbers is 80. So this is what it looks like. So this is what I'm looking for. This is the secondary. So y is equal to 80 divided by x. So then substitute that in. That's the minimum we're looking for. So this is x plus 400, x to the negative 1. Take the derivative of that. 1 minus 400, subtract 1. There's the derivative. Make it equal to 0. So how I would solve it is I would add 400, and then x to the negative 2 becomes positive 2. You draw it right as a fraction, so x squared goes in the denominator. So I added it, and then I cross multiply or multiply both sides by x squared. When you take the square root, then the answer is 20, only the positive number. So the last thing I look at is if this creates a minimum. So into the derivative, if I plug in positive 1, you get a negative answer. If I plugged in 1 billion, I would get a positive answer. So it goes negative to positive. So 20 is a minimum. So x equals 20. Y is 80 divided by 20, which is 4. So 80 divided by 20, which is 4. So the first number is 20, and the second number is 4, so that the sum is a minimum. So that's an optimization question. Last question for the assignment, 22. In 22, it says use the number lines. So let me draw them. So we have a first derivative number line, 0 and 2, negative, positive, negative. We have a second derivative number line at negative 2 and 0. And it says use those and sketch a possible graph of a continuous function f using those. So we don't have a starting point. So let's see what we can do and understand. So obviously from negative 2 to positive 2 is important. So let's just do that. From negative 2 to positive 2. What do we know? We know at 0 is a minimum and at 2 is a maximum. So I'm going to create my minimum. Somewhere down here, it's got to be lower. Did he give you any other information? All right. So I know that's a minimum. I know at positive 2 is a maximum. I know at negative 2 there's a point of inflection somewhere there. And I also know at 0 there's no point of inflection. So how would I connect these? So these are the important points that are going to connect together. So first of all, it is decreasing to 0. So the first, it decreases with a smile. And then it decreases with a frown. So it decreases with a smile. Then it decreases with a frown. After 0, it increases up to 2. So from 0 to 2, how do I connect it? It's frowning again. So it's frowning. And then what happens after 2 is it continues to frown, but now it decreases. So does this match? Just double check. It's decreasing to 0, increasing to 2, then decreasing. It's concave up, concave down throughout. So it matches, and there's a sketch using the derivative lines. Not easy, right? That's why we have to keep practicing it, the conception of it. All right, Mr. G Math over and out. I'm proud of you for doing your work. Until next time.